collision problem. Last time, after we discussed two hash function methods, division method and the multiplication method. And we know multiplication method is better than division method. Why we treat it better than the division method? Because when we choose some irrational number as the constant to do multiplication, modular operation, we have better chance to break given patterns. So here, because the given data, they may focus on patterns. So we want to break it. Okay? So that's our goal. And we feel, although we couldn't prove, but we feel multiplication method, we have better chance to break the patterns. But at the end, we made a conclusion. The conclusion is there is no perfect hash function. Nobody can define some perfect hash function. So what do you mean perfect hash function? The meaning is for any two different keys given, the hash function can map to two different locations. That's perfect. But it's impossible. Nobody can do that. Then we need to deal with the collision problem. Because we may have some cases that we may map different keys to the same location in the hash table. B.1, collision problem in hash. Resolving collisions by chaining. So here, I just give you a few simple ideas. And you mute. Forgot to mute. Yeah. All right. So some simple method. The first one, chaining method. Resolving collision problem. Assume that multiple keys are hashed into the same slot in the hash table. When it happens, the first straightforward method, we just create a linked list. Chain. We create a chain. We attach a chain to that particular slot. All the elements hashed to this slot we put in this linked list as a chain, straightforward way to resolve the collision. So in the diagram, suppose this is our hash table. Okay? So we have certain number of slots. All right. Yeah. Associate each slot with a linked list. All right, so like initially empty. Initially, each one associated with an empty linked list. Then, when you think about it, the first element hashed into the slot, you do not even put a linked list, right? Because there is no collision. You just put a normal slot, a normal place. The first one, no collision, empty. It's an empty slot. So you just put there, okay? All right. When you have the first collision, for example, this is the first collision. Yeah. So you cannot it in a normal place, then you put it as the first element in the linked list. This one, you have two elements hashed to an occupied slot. Yeah, this slot already occupied. Okay? But later, you happen to hash two more elements in the same location. So there you put, in the linked list. Okay? So that's the idea. That's the chaining idea, the first method. Yeah, so the longer the linked list, the poorer the performance. If your hash function is very bad, then some of the linked lists could be quite long. Okay? Then your overall performance will be bad. Okay? Overall performance will be bad. All right. But this is a solution. This is a solution. Okay? Yeah. All right. So the worst case for this solution, the worst case, big O of n. Big O of n. Although in general we won't have that. Okay? Yeah. So that pretty much you hash large number of elements. Okay? Large number of elements in the same slot. Okay? Think about if we use the multiplication method. We should not have this bad performance. The best case, big O of 1. Big O of 1. Okay? The linked list is very short. Typically, 1 or 2 elements in the linked list. That would be good. That would be pretty good. Okay? Small, relatively small number of elements in each linked list. Okay? For the average case, big O of 1. Okay? Average case in this way, also big O of 1. Okay? Average, spread out, but make sure your hash function is good enough. If we choose a good multiplication method, yeah, that A, a rational number A, to try to break the general patterns. We don't know if we can break all patterns. It's impossible. But most of the patterns we can break. Then we can have the average case efficiency big O of 1. That's the overall performance for the hashing technique. Why you can big O of 1, right? So you may wonder at the beginning, because this performance beats the binary search. Binary search, big O of n log n. Better than the binary search. Binary search is very powerful. Very powerful. And this method easily beats the binary search. How can that happen? After you get to this point, you understand why we can get this good performance. Okay? All right, now, so this is the first collision resolving method. Linked list, because we know usually people like to avoid linked lists, right? People like to avoid. If it's possible, we try to avoid. Right. So we want to look at other solutions here, because here my my objective for this part, give you some general introduction. I don't want to go too far, too deep on this topic. Okay? Just give you some general introduction. All right, so measure average number of elements in a chain. So we would like to, if we want to do a little more analysis, we like to introduce a special measure related to the chain. So there is a concept called a load factor. Load factor. You load an array of elements into your hash table, so there is a load factor. Okay? Related to the number of slots in your hash table and the number of elements in your array. So we define alpha, load factor. So what's the alpha? Here, assume we have a hash table T. Okay? So this T has n slots. N slots. Okay? And we want to map n elements, n element array into this hash table. N elements. Okay? So these two numbers, we can consider a ratio. Alpha equals n over n. N over n. That concept we call a load factor of this hash table. So you can see, if we spread n elements evenly into these n slots, each one should be assigned this alpha, this many elements. Because we can use a linked list to hold this many elements. Okay? Yeah. So that's the measure. So you can get an idea how much loaded is the hash table. You can get this idea. So average number of elements in a chain. That's the measure. Alpha. Okay? Yeah. If it's less than 1, yeah, actually we like to less than 1. Yeah, because if it's less than 1, we do not have severe collision problem, right? It's on average less than 1 element in each slot. Actually in the chain. Average. Can you see something? Because think about it. If we consider each slot there is a normal location, then linked list, right? If we understand it that way, -1. There is a -1. But it can give you the how many elements map it to the same slot. We can understand it that way. One slot, because there is a linked list attached to it. Okay? There is a regular slot and one linked list attached to it. All right. Equals 1. Equals 1, so average 1, ideally all the slots are occupied and no elements in the linked list. That would be the perfect hashing case. Okay, equals 1. Greater than 1 is allowed. Greater than 1, because we just grow our linked list. So greater than 1 alpha is also allowed, but you expect to have a little more collision problem. Okay? The higher this number, the worse the collision problem. The slower your search algorithm. Okay, so you need to control that. Do not make that alpha too big. Okay. Do not make it too large. Yeah. All right. Yeah. Simple uniform hash assumption. Any given element is equally likely to hash into any of the M slots. If no specific pattern, right, then you have this uniform hash, simple uniform hash. It's like uniform distribution. Okay? In statistics, it's like, the elements come in the uniform distribution. That's the best thing we can get. Okay? Yeah. So evenly distributed in those M slots. All right. Independently of where any other elements has some chat message. Let me check it. Yeah, right. Yeah, Amanda. Yeah. Open hashing. Right. Yeah, different names. Actually, open addressing. Yeah. So we will talk about that open addressing problem. All right. Oh, so here you can see when I do some action here. My PowerPoint slides freeze. I need to get out of it. Then get in. Yeah, open addressing we will talk about next one, not this one. All right, this chaining one, different. So let's finish this one first. All right, average case, big theta 1 plus alpha. 1 plus alpha. Okay? All right. Yeah. Next one. Yeah, so that's Amanda talk about open hashing, open addressing. Resolving collisions by open addressing. So this is another simple way. But this way, we want to avoid linked lists. Right? We don't want to deal with the complexity of the linked lists. So let's just use the existing slots. But we want to make sure the number of slots should be greater or equal to the number of elements. That means we have plenty of locations for a given array. Okay, given array. Plenty of locations. All right. Do not use the linked list. Elements only occupy the table slots. But we need to find a way to assign the vacant slots. So here, this method, open addressing, straightforward, very simple. Okay, so let's see it. No space outside the table is used. For the previous one, linked list, that's the space outside the table. Outside the table, right? All right, yeah? So we require alpha less than or equal to 1. Then you can use this method. It's easy. You just make your n number larger, the slot number larger than the number of elements in the array. That's simple. How to handle a collision? some simple algorithm. When a collision occurs, we want some simple algorithm to find the next vacant slot. Okay? Find the next available slot in the hash table. There are many different ways. Here I only want to talk about one way, first way. Second, third becomes harder and harder, but the performance would be better and better. Better and better. Yeah, but here I just give you some general idea. So we do not need to go that far. Okay? All right. Probe sequence, this concept. Probing. Probe. We need to find the next available slot. So we need to do probing operations. So what's that? Yeah. Keep going, apply our hash function again and again. Yeah. All right. When a collision happens, the slot at h of k is not available. Yeah. Here, for example, in this line, we have certain number of slots. Okay, all right. The first time we apply our hash function to map h of k in this location, in the first location. And when we check the slot, if it is empty or not, we find it is occupied. Okay, it is occupied. Then we cannot use the slot. We have to look for the next available slot. But question, how do we move to the next available slot? Sequential way, right? Just look at the next slot, okay? Adjacent, next slot. Look at, if occupied again, another, next one, another, all right? Yeah. That's the simplest way. It's simple. The performance won't be good, but it's a solution. Until, because eventually you will get it. Empty one, right? Sooner or later, you will get an empty one. Then you occupy it. That's simple. If you're not lucky, you may need to, check multiple places. Okay? Yeah. Many slots you need to check. Okay? Occupied. Yeah. Then find an empty one. Then sit there. All right? Yeah. Eventually, a vacant slot. Yeah. Because n greater or equal to n. Okay? Any element, you can find a location for it eventually in this way. Right? Yeah. All right. That's the simplest, straightforward way to resolve the hash collision. The general formulation for the sequence of location. Yeah. So here, what's the meaning of probe sequence? We consider a sequence of locations in this one. This sequence gives us the location to check. So the first one, second one, third one, one sequence. But we need to define this function. This function, you can see, it's a two-parameter function. First one, k, hash key, right? Given key. But second, we need another parameter so we can control the number of steps we take to find an available slot. All right. So this is the probe sequence definition. Properties of a probe sequence. Because you can define your probe sequence in many different ways, right? In the previous slide, we haven't defined. Here, we can write many different definitions. All right, but when we write a definition, we should follow these properties. These properties. The sequence should cover all the slots. You cannot have, some slots, the sequence, you skip some of the slots. Then it's not acceptable. Okay? Your definition of the probe sequence is not acceptable. Right? Yeah. Cover all the slots. Right? So it should be a permutation of these numbers. The slot location, indexes. Let's say slots, we can use their natural indexes, 0, 1, 2, up to n minus 1. Their natural indexes. All right, it should be a permutation. Okay? Yeah. All right. The simplest probe sequence definition, we use this simple formula. Just +1. Okay? Each one, we use the previous value +1. So we can simplify this location because it will cover all the slots. All the slots. Yeah. So satisfy, the minimum property. All right. But is it good or not? It's definitely the simple way. Overall performance won't be good in general. Won't be good in general. So why won't be good in general? So I will explain. Some problem here. Linear probe. Linear probe. All right. Because think about when you have certain number of slots occupied, then your collision problem will be worse and worse, right? When you have certain number of consecutive slots are occupied, then the performance will be worse and worse. So here, a slightly better way is linear probing. So we don't want to just look at the next adjacent location. We want to jump in different ways. Jump a little bigger. So here we need an auxiliary hash function, h prime of k. Auxiliary function to help us control the locations. We want to do a little better. We want to do a little better. So we define our probe sequence with a new definition, with this auxiliary function and the original hash function, two functions to define that probe sequence. How to define? We define this way. H of k comma I equals h prime of k plus I mod n. Mod n. Okay? Yeah. Here you can see we have a chance to change the hash function values. Probe sequence, yeah, here it's linear probing. Yeah. The k part, and I part, two terms adding. Yeah, actually this is linear probing. Yeah, this I 1, 2, 3, right? 1, 2, 3. Yeah. This is just a formulation of our previous one. But this one, if you like, we can change. We can change the way we define the next slot. All right. The main problem of this method, primary cluster. Primary cluster. Cluster. Okay? Many elements are mapped to locations clustered at some place. Cluster. There is a cluster. Cluster of slots are all occupied. Okay? If you want to get the next available slot, you have to pass this whole cluster. Whole cluster pass. But it takes a few tries to pass the cluster, right? Think about it. You have some relatively big cluster here, right? When you map the first key here, in order to pass, you need to try, many times before you find some available location. That's the biggest problem of this one. So here we call it primary cluster problem. And you may have secondary clustering problem. Secondary clustering problem. Okay? Linear probing would result in primary cluster. Now we have an improved method called quadratic probing. We can improve on this primary clustering, but that would result in secondary clustering, still clustering. But slightly better, not primary, secondary. So here, just to let you know, actually, if you want to find a very good solution to resolve collision problem, not easy. Not easy. Okay? All right. Okay, yeah, primary cluster. Okay? Primary cluster. Okay? Yeah. If a hash value hits a cluster, we have to go through long runs of occupied slots. That would result in bad efficiency. Bad efficiency of this algorithm. Okay? Yeah. All right. Okay, yeah. So for hashing, I just want to stop at this point. Okay? Yeah. So that should be enough for your general introduction. Okay? General picture in your mind. If you are interested in this topic, you can dig in deeper, study by yourself, deeper. But you have this background, you just use the existing hash table data structure, right? In Java, we have hash map. Remember, last time we have a class called hash map, Java class. You just grab this class and store the elements with given hash keys. Okay? Put, the method you use called put and get. Okay? Get will retrieve the element from the hash map object. Put, you store an element into the hash map object. Yeah, then perfect. To understand the underlying implementation, this background information should be enough. Okay? This is the background information you have. Okay? So you will feel comfortable to use this data structure in Java. Okay? All right, so let's move to the next topic. All right. Now, because after you finish this class, this topic is important. So here, I only have half an hour, so I want to complete this topic. Still a lot of material for this topic. Lower bound of comparison-based sorts. So here, I only talk about comparison-based sorts. Sorting algorithms, but we use our basic operations as comparisons. I use comparisons as our basic operations. You may wonder, other than comparison, can we have other different ways to do the sorting, right? Think about that. Without using comparisons, do you have other ways to do sorting? Right? You may think this, yes. Actually, because after today's class, we only have 2 classes left, right? Yeah. And we would like to use those 2 classes on review. Okay, 2 classes left on review. Comparison-based sorts. There is another interesting sort we call counting sort. Counting sort. From its name, you can see we do not do comparisons. We do counting. We can sort. But the counting sort, if we do counting sort, then your array elements must be integers. Must be integers. Your array values must be integers. Then you can count number of integers. If it's floating point numbers, then you cannot apply this algorithm. Okay? So it has limitation. The counting sort, you have some constraints. You have to follow a few constraints. Okay? So integer is 1, then the range number is another one. Range. Alright? Yeah. The integer, if the range is too large, then counting sort won't be good. Okay? The range cannot be too large. Under those 2 conditions, the counting sort, we can do very well. Okay? The counting sort, you can get a big theta of n efficiency. You don't do comparisons. Counting sort, you can get, but with constraints. When we use comparisons, we don't have constraints, right? We don't have constraints. Okay? So here, I just want to know the difference. The difference. If I can find time, I'd like to talk about that. Or another options I can do, I record some videos, and I don't use class time. I just give you video links. If you want to watch, then you can find time to watch it. But you do not have to spend time. All right, let's look at this question. Lower bound of comparison-based sorts. All right, I need to do a little fast here because I want to finish it in about 25 minutes. So a lot of things I want to talk about here. The first thing, that lower bound, based on our existing knowledge we have at this point. So now we do comparison-based sorts on n elements. Okay, all right. Here, lower bound. First, let me give you the lower bound first. Then I will derive, I will use some fancy way to derive this lower bound. Then we complete the whole story. Okay? Yeah. So first, when we start, I give you the lower bound. Lower bound formula. Okay? Floor function of log base 2 of n factorial. How about that? Lower bound log base 2 of n factorial. N factorial. Okay? Yeah. All right. So let's check. Let's, check this formula. Because we have some information already. Yeah. When n equals 3, we know to sort 3-element array, for the worst case, the minimum number of comparisons 3, right? Yeah. So that answer, we know the answer is 3. Okay? Yeah. The minimum number of comparisons, 3 comparisons. Okay? Yeah. Now let's look at it. Floor function log base 2, 3 factorial. Oh, sorry. Not floor function, ceiling function. Yeah, because when I use 3, I notice, ceiling function, not floor function. Yes. Yeah.
Just to clarify, is it natural log or is it log base 2?
Log base 2. Okay. Here in computer science, LG means log base 2.
Not log base E.
Yeah, log base LN, natural. Yeah. All right. So here, let me write this way. Okay. Ln base E, Lg base 2. Okay? Yeah. But this is the CS way. Okay? CS context. CS context. Math context, Lg becomes base 10. CS context. Okay? All right.
Thank you.
Yeah. Yeah. Yeah, it could be confused. Log base 2 of 6, right? 3 factorial 6, then you get 3. Okay? Then, n equals 4. So we did it before, the answer is 5, right? Answer is 5. But what is the ceiling function log base 2 of 4 factorial? Okay? Ceiling function log base 2 of 24, right? 24 greater than 16, less than 32. So it is 5, right? So the same number. So let's try another one. N equals 5. I did in one video, right? One of the problem solving videos I gave you before, the answer is 7, right? Answer is 7. We did it in 7 comparisons. Let's see the ceiling function log base 2 of 5 factorial. 5 factorial equals 120, right? 120 greater than 64, less than 128. 128, 2 to the 7th. All right, so ceiling function is 7. And so on. So you can, here you can see after we check these first 3 cases. Works well, works well. The next question, how do you find this formula? How to see it? It's not easy. It's not easy. Okay? Here, we need to use a special technique here. I want to introduce the technique here. Okay? It could be useful for you in the future when you do analysis. When you do algorithm analysis, this method could be useful. It's called decision tree method. Decision tree method. What's that? Decision tree. You draw a decision tree. You make decisions. Okay? Based on the results of the decisions, you go to different branches of a decision tree. Here, each node, a node of the decision tree corresponds to a comparison. Okay? Okay? So that's why we use this technique to study comparison-based sorts, sorting algorithm, sorts. Okay, all right. Yeah. What's that? When we do comparisons, compare A and B. We want to categorize the results in two categories, not three. Okay? Three, not two. Because we want to draw binary trees. So we want to have two different categories. All right. So one is A less than equal to B. Equal, so we put together with less than. Okay? Another one is A greater than. Okay? Because in this way, we can draw a binary tree, not a ternary tree. Okay? Otherwise, ternary tree. Here, we want to draw binary tree. Okay? Yeah. All right. Then we can draw decision tree. To draw decision tree, so to show you, let me draw. So here, let me draw the decision tree for sorting a 3-element array. Okay? Yeah. 3 elements. Let me write x1, x2, x3. Okay? Let me show you how to draw a decision tree. Okay? All right. And the root node. Root node corresponds to our first comparison. Our first comparison, here I write this way. A1 colon or x1 colon x2. That means we do comparison on x1 and x2. So we should have 2 results. Okay? Left, x1 less than or equal to x2. Right, x1 greater than x2. Okay? Yeah. If x1 less than x2, what's the next comparison you'd like to do? Okay? You may like to compare x2 colon x3. Okay? Yeah. So you have two cases, x2 less than x3 and x2 greater than x3, right? x2 less than x3, you get sorted, right? Yeah, because after you follow this decision tree location, so we use a box to denote the array is sorted. The order is x1 less than equal to x2 less than equal to x3. Sorted. But if x2 greater than x3, we need to compare x1 colon x3. Right? Yeah. So now you have two cases. Left x1 less than or equal to x3, right x1 greater than x3. Okay? Yeah. If x1 less than or equal to 3, can you get array sorted? So you use a box to denote the sorting result. The smallest is x1 less than or equal to x3 less than x2. Right? Yeah. If x1 greater than 3, the array is sorted, and x3 smallest less than x1 and less than equal to x2. How about that? Okay? This is the left half. The right hand half, can we do the similar thing for the right subtree? Right? So here I do not need to repeat it. Okay? Yeah. So good, similar way. In this way, we can draw a decision tree. Alright, so here. Now we want to use this decision tree, give us estimate. Give us the estimate for the lower bound of the comparison-based sort. Alright. But next, we should generalize the 3-element array to n-element array, right? With array elements x1, x2 to xn. Okay. Can we draw similar decision tree? It could be very complicated, but there must be one corresponding to sorting any algorithm that sort an element array, right? Yeah. Think about it. No matter what comparison-based sorting on this n-element array, you will get first comparison, second comparison, and so on, right? So based on your first comparison, second, all the comparison details, can you find a corresponding decision tree for it? Think about that. Think about that. Yes, the answer is there must be a decision tree corresponds to any sorting algorithm. Okay, so here, to save time, I do not write this thing. Okay, so there must be a decision tree for any comparison-based sort with n elements. Yeah. So that's our first step. Second step, sorting result. We want to study the number of sorting possibilities. The number of different sorting possibilities. Yeah. Look at here. The boxes I draw, 3 left-hand side, another 3 right-hand side. Total 3 plus 3, 6 different sorting results, right? For 3, we have 6 different sorting. Is it 3 factorial? Is it 3 factorial? Right? All different possible sorting results. For n element, should we get n factorial different sorting results, n factorial. And this n factorial number we can interpret as we have the number of leaves of the decision tree. Here, let me write. The number, there are leaves, right? Yeah. So you know the meaning of leaves. The number of leaves of the decision tree is greater or equal to n factorial. Here, I do not write strictly equal. I write greater or equal. At least cover these n factorial. Why I put that greater case there? The reason is simple. Your algorithm could be redundant, right? Because someone designed a poor algorithm. Yeah. So when you move to different branches, you get same result, right? So the same box appears multiple places. That could happen, right? Yeah. So that's why we get greater or equal to n factorial. Number of leaves. Number of leaves. Yeah. Here, let me use a notation. Leaf number. I use capital L to represent number of leaves in the decision tree, capital L. Okay? Yeah. Capital L greater or equal to n factorial. Then, our last step, we want to make conclusion quickly. Last step. All right. Here, I just draw a general decision tree. Okay? General decision tree. Okay? All right. Yeah. General decision tree. All right. Yeah. Okay. We know capital L, number of leaves. Number of leaves. Yeah. Here, not necessarily all the leaves are the same level. It could be there is some leaves higher. Okay, yeah, it's possible. There are some leaves, level a little higher. Okay, yeah, it's fine. Yeah. So we also count it as in the capital L. All right. Now, we want to get the worst case efficiency. Because our goal, we want to find worst case efficiency. From this tree, can you see what concept corresponds to the worst case efficiency?
The leaves at the bottom level?
When you do comparison, you start from the root, then you follow certain paths until you reach the bottom. That's the way how you do comparisons. How you do a sequence of comparison. When you reach the bottom, you find the result. Can you see how many comparisons you want to do for the worst case? What's worst case? You start from the root. You end somewhere at the bottom. Is it the concept of height? Height of the tree? We call height of the tree. Okay? H. H equals the height of the tree. The whole tree. Height corresponds to the worst case. Responds to the worst case. Okay. All right. Okay. Then, next step. Now we're close to the conclusion. Closer and closer to the conclusion. Here. Height estimate. So here, let's estimate height. Here we need to find a relationship between L and H. For a binary tree, can you have a relationship between H and L? H and L, some relationship? We need that. We need this relationship to estimate H using L. H using L. Okay? So we need this relationship. All right. Now, imagine to get this relation. Imagine what? Here, we draw a complete binary tree. You know complete binary tree, right? Draw a complete binary tree. Okay? All the levels are full. Yeah. You know, including the bottom level, all are full. Okay? This is a complete binary tree. Okay? All levels are full. Okay? And suppose we have a complete, so here it's a complete binary tree with height h. With height h. Okay? Here, can you tell me what is the leaf L number? The number of nodes at the bottom level. Height h complete, L number of leaves at the bottom level. Can you see that? Relation L and H. L equals 2 to the H. Power of 2, 2 to the power of H. That relationship. L equals for the complete binary tree. Now we go back to the non-complete general binary tree. General binary tree, we won't have as many leaf nodes, right? Yeah, because some of the nodes moving upper levels, then we should reduce the number of leaves, right? When you move higher, the number of nodes will be reduced. So your L number will be reduced. So for the general case, L less than equal to 2 to the H. How about that? The general case, L less than or equal to 2 to the H. And we know L greater or equal to n factorial, right? From the previous slide, we know L greater or equal to n factorial. Can we take log of base 2, both sides, log of base 2, n factorial, less than or equal to h, the worst case efficiency, but usually log of function is not integer, right? To make it integer, we take ceiling function, less than or equal to h. How about that? Ceiling function. So is this the lower bound? Because any h should be greater or equal to this function. So that must be a lower bound. So we derive it. Lower bound. Okay? Yeah. Lower bound. Then, last minute. Okay? The last question. Although here we have the lower bound, that means when you do a comparison-based sort, you can never do better than this number. Okay? You can never do better than this number. This number minus 1, nobody can do it. this number minus 1, nobody can do it. Okay? No matter how smart, how powerful, nobody can do it. This number minus 1. But the question is, there's still unknown question. Can you reach this number? That's the question. Okay? Yeah. In our A equals 3, 4, 5, we reach it, right? 3, 4, 5. Sorry, 5. We did it. We reach it. We reached that number. For A equals 6, we don't know. A equals 6, because for me, I've never seen someone do A equals 6. The minimum number of comparisons. Extremely high. I cannot do it. Okay? I wish I can, but I couldn't. A equals 6. So people don't know if they can reach this lower bound or not. All right, so let's stop right here.